Oh, hey, Emma, how's it going?
Oh, hey, Professor Ledger. It's going really well. I actually just got this camera for my birthday. I used to only have a cell phone camera, but this takes much better pictures. It has variable aperture, 6 frames per second, telephoto lens. It's pretty awesome.
Well, I guess that's pretty good.
Pretty good? This is one of the best cameras that money can buy. It's a little bit better than pretty good.
Yeah, but it's so big. I mean, what if someday we could make a camera that had the same quality pictures but was really thin and weighed almost nothing?
That would be pretty cool.
Well, that's just what we're working on in my research lab. You want to come up and take a look?
Yeah, sure. Let's go.
So this is one of my coherent optics labs where we do research on lasers and image science. The project we were talking about downstairs is being run by Jordan Birch, one of my graduate students. Let's go meet him.
Okay. So Jordan, Professor Ledger tells me that you've been working a lot on this camera. Can you show it to me?
Sure. This is it.
Oh my gosh, that's a lot smaller than my camera.
Quite a bit.
So can you tell me a bit more about how it works?
Certainly. Before I talk about my camera, it's probably a little helpful if I talk about your camera first. Let's say you're taking a picture of a cat, and you've got your camera with a traditional lens. Light bounces off your cat and gets reflected into the lens, where it then forms an image on the back sensor of your camera. The problem is, for this to work, your lens needs to be rather thick and therefore heavy. My camera uses something called a waveguide, which you can think of as a sandwich of different materials. On one of the sides I've etched a pattern, which is called a grating. Now say you're taking a picture of the same cat with my imaging skin. Light bounces off the cat and is reflected on the waveguide surface. The grating then diffracts the light into the waveguide, where it bounces up and down until it reaches the detector at the far edge. And you can use this to build up the image. The advantage of this type of system is that my camera is very, very thin. In fact, the active part of the camera is only 3 microns, which is less than 1/10 the thickness of your hair. Because it's so thin, it means it's very light, and that opens up all kinds of possible applications. You could think of these cameras falling from the sky like confetti, where each one ends up forming a different image as they fall. Or, say you have robots that are the size of insects, but wings of the insect actually are the cameras themselves.